Hello everyone, welcome back to another OneClass session. Today we're going to be going through some physics problem. My name is Bassam. I'm an engineering graduate, and the physics problems that we'll be going through are at the high school level and the preliminary university level, or kind of the level 1 physics in university. So let's get started. So the first question here is asking, what is the linear mass density? So we can kind of go through the concept here. So we can represent linear mass density. Often it's represented by lambda, and it's some mass over some length. So m here is mass, L is length. We can kind of draw a plot. So let's say we had some linear object, so like a string or something. And we have y and x, and we have some unit, small unit, dx. So this small unit, you can say that the mass, to evaluate for the mass of this entire length, we'd have to evaluate the integral of dm, of each unit of mass along this length. And then dm here, kind of using this formula up here, we can say that m is equal to lambda dx, because we know dm over dx is equal to lambda. So we just rearrange using kind of this equation above, and then we can kind of use this to evaluate for the integral if we were given this type of question. But essentially here, the linear mass density is kind of just the density across a linear object, or it's a linear measure. So we have some kilogram, let's say, per unit, so kilogram per meter or something like that. So here they use different variables. So they use lowercase m for lambda, uppercase m for mass, lowercase l for length for the attempted solution. So find the linear density of a wire which is 3 meters in length and 3.5 grams in weight. So here you see, you just substitute in the values and you get the linear density in grams per meter. So they also outline what is density. So density is mass over volume. So a similar measure of density. Here we only care about linear mass density. You can see they evaluated it similarly, just substituting in the values. And density and concentration related. So this isn't really related to the question. As long as we understand what linear mass density is, we're fine. So correct solution. Great job. Let's go on to the next question. So the next question is asking, a car traveling with constant speed travels 150 kilometers. What is the speed of the car? So it's telling us it's constant speed. So we can use the equation v is distance over time. And the distance here is given to us as 150 kilometers, so we can just substitute in that right away. And the time is 7,200 seconds. So usually the units you want to represent the final answer in is usually either kilometers per hour or meters per second, depending if the question states it that way. So we can just evaluate this right away and just see how many kilometers per second that is. So we get 150 divided by 7,200. That'll give us 0.0208 kilometers per second. So this isn't really a clean number or an easy kind of number to remember. So we can kind of try to convert this into kilometers per hour. So we'll write this down here, 150 kilometers over 7,200 seconds. We'll multiply this by, so in one hour, we have 3,600 seconds. To get 3,600 seconds, essentially you have 60 seconds per minute, and then you have 60 minutes per hour. So you do 60 times 60 will give you 3,600 seconds. And then this will give you 75 kilometers per hour. So that's the speed of the car. We can also convert 75 kilometers per hour into meters per second if we wanted to. And to do this, we multiply by, so I'll just keep going further over here. So we multiply by 1 hour over 3,600 seconds. And we also multiply by 1,000 meters per kilometer. So we can see the kilometer cancels out, the hour cancels out, and then we're left with the 1,000 on top and 3,600 on the bottom. So to evaluate this, we do 75 times 1,000 divided by 3,600. It's 20.83 meters per second. So most likely this question would ask you to write in kilometers per hour because this is a whole number while the rest is giving decimal places. So our final answer is 75 kilometers per hour is the speed of the car. So looking at the solution, they go through the similar process. So 150 kilometers divided by 7,200. This will give us the speed in kilometers per second. We want kilometers per hour, so they do the same conversion rates to get kilometers per hour. So solution is correct. Great job. Okay, so what is the impulse on a 3 kilogram particle that experiences the force shown in the figure? So I'll just give this a second to load. I think there's a figure that's going to pop up. Yep. Okay, so we're given this figure. We know that there's a particle, weighs 3 kilograms, and we have to evaluate the impulse. So whenever we're given a diagram that's in the format of force times time, to find the impulse, so impulse is represented by the variable j. So j is equal to ft. So to evaluate it from a graph, we just have to take the area below the graph. So give me a second actually. So actually, j should be equal to the integral of force dt. Okay, so if we're evaluating it for this plot. So to do this, essentially we see that there's 3 triangles. If the triangle is above the x-axis, we know it's a positive component. If it's below, it's a negative component. So we'll do each triangle separately. So we'll say J1. So J1 is this one, and then J2 is this one, and then J3 is this one. So this will equal to a half base times height for the area of a triangle. So the base here we know is 2 units. So I'll just write the area of a triangle as a half base times height. And the height here is negative 500. So this will give us just negative 500. So we should pay attention to the units. This is in newtons and this is in milliseconds. So this is Newton milliseconds. And then the next one, J2, is a half. So the base is 8 minus 2. So 8 minus 2, which is 6. And the height is 2,000. So this will give us 6,000 Newton milliseconds. And then J3, which is the last triangle, is a base of 2, so half times the base, which is 2, times negative 500, which is the height. We also get negative 500 Newton milliseconds. So all we have to do is just sum up, just add up all of these together, J1 plus J2 plus J3, and we end up with 5,000 Newton milliseconds. We can just convert this into Newton seconds, and that would be divided by 1,000 to get Newton seconds, because there's 1,000 milliseconds in 1 second. So 1,000 milliseconds in 1 second, we divide by 1,000. So that's our final answer. Let me just write that a little more clearly. So 5, and our final answer is 5 newtons seconds for J, for the impulse. So they have the same equation, J equals Ft. They go through, calculate the area of the triangle, and they get the final answer of 5 Newton seconds. So the solution, the attempted solution by the student is correct. Great job. Let's go to the next question. Right. Okay, so true or false, most conducting materials have different resistances at different temperatures. So the answer here is true, but let's try to think about what this means. So for all conducting materials, we have this thing called a temperature coefficient. And what this essentially tells us is, let's say if we had a high temperature, in a conducting material, we know that there would be more collisions, because a high temperature means more kinetic energy. So there's more collisions between the electrons. So this means more collisions. And then because there's more collisions between the electrons, the flow of the current will decrease. And this is due because this increased temperature causes an increased resistance. And this increased resistance is represented by kind of the increase in collisions, which decreases the flow of electrons. And then this kind of decreases our current flow, and we'll represent current flow by I. So here we can see when we increase the temperature, there will be increased resistance. And all conductors have a temperature coefficient that relates this information to us, how temperature affects the resistance of the material. One thing to note for the temperature coefficient is if the temperature coefficient is positive, this means that the relationship, so an increase in temperature, means there will be an increase in resistance. So I'll just make a line, separate this out. Secondly, if the temperature coefficient is negative, an increase in temperature means a decrease in resistance. So most conducting material have a positive value, but in some scenarios there's a negative value for the temperature coefficient, and that means we'd have an increase in temperature, we get a decrease in resistance. So this thing is true, most conducting materials have different resistances at different temperatures. So looking at the answer, each type of material known for its high conductive quality has a different temperature coefficient. This is the material susceptible to heating, or how much its resistance rises with temperature. And then outlines most materials have a positive temperature coefficient, and this impacts the resistance of the material. So correct answer. Great job. So we'll clear this and go to the next question. Okay, so let's read this next question. So a rescue plane wants to drop supplies to an isolated mountain climber, a rocky ridge 235 meters below. So we're in a plane and we're trying to send supply to someone 235 meters below. Assume the plane is traveling horizontally with a speed 210 kilometers per hour or 58.3 meters per second. So I'll just draw a diagram to represent what we know. So we have a plane. So this is the plane. And we have some person over here. So this is not scale, obviously. Let's say this is the center point of the plane. And we have this person, the center point, or the point where he is at, is right there. Okay, and we're going at a speed of 235. Oh, sorry, 8.3 meters per second. And we're at a height 235 meters. And we're asked to find in the first part of the question, so I'll just go part by part, how far in advance of the recipient's horizontal distance. So we're trying to find, if we were to draw this down, and if we were to draw the horizontal distance, and let's call this x, we're trying to find what this is. How far in advance of the recipients must the goods be dropped so it can get to that person? So this is a kinematics question, and we need to use the kinematics equations to solve for this question. So some values that we're given is the height and the speed. So the first kinematic equation we should use is delta d equals vi, so the initial velocity times time plus a half acceleration t squared. We know that gravity is acceleration and it's pointing down. So let's define a coordinate system. So this will help us. I'll just say positive x in this direction and positive y in this direction. And we know gravity is 9.8 meters per second. So we're going to use this equation to solve for time. The main reason we're doing this is in the horizontal direction, it's traveling at a constant velocity. So the kinematic equations only apply when there's an acceleration. So when there's constant velocity, the acceleration is 0. So we can, when the acceleration is 0, we can just say velocity is distance over time. But in the y direction, we know that the acceleration is due to the force of gravity, which is 9.8 meters per second squared. So we got to use the kinematic equations. So delta d, so from the plane to the ground, is negative 235 meters. So the main reason we use a negative sign here, so the negative sign is important because it'll kind of mess up the value if we don't put it incorrectly. So we look at the final location and where we're starting from. So the final is 0, and we're at 235 meters, and the package is going to land at 0. So final minus initial will give us delta t. So 0 minus 235 is just negative 235. And then vi, so the initial velocity when we drop it is just 0. And we have time, and plus a half. Acceleration is negative 9.8 meters per second squared. So because acceleration is pointing down, we put a negative sign. The package is going down, so the change in distance is negative. It's going downward. And t squared. So here we just have to solve for time. The reason we want to solve for time is because we know we can plug it into this equation, and we already know the velocity here because it's given as 58.3 meters. And we can solve for d, which is just x in this scenario. So we have negative 235 equals, so a half times negative 9.8 is just negative 4.9 t squared. The negative signs cancel out, and we're left with t equals square root 235 divided by 4.9. And then this will give us, so we do the square root of 235 divided by 4.9, 6.925. seconds. For an S. Okay, so we figured out the time it would take when we drop the package till it gets to the person. Now we're going to use this value because we know it's the same for the X and Y direction, because the package will get to that person in the X direction and Y direction at the same time. So we know V is d over T. D in this scenario is X, and here, let me write that again. So we know V is 58.3. It was given in our question. D is X, and T is 6.925. Solving for X, we have 58.3 times 6.925. That'll give us 403.7 meters. So that's answering part A. So this is part A. Let's look at part B now. Suppose instead that the plane releases the supplies a horizontal distance of 425 meters in advance of the mountain climbers. What vertical velocity, up or down, should the supplies be given so that they arrive precisely at the climber's position? So we can see we're dropping it 425 meters away in the scenario in B. So for it to get to the climber at the scenario in A, we have to be 403 meters. So if we dropped it earlier, 425 meters away, we need to figure out what initial velocity should we be starting out at. And we kind of think about this conceptually. So for further, that means our initial velocity should be upward. So we need to throw the package a little bit upward for it to land at that person because we're a little bit further away. If we dropped it at the same spot, that means it's not going to reach the person. It's going to land like a little ahead of that person. So let's just go through the equations. So we're going to use the same kinematic equation. So delta D is VI times T plus a half AT squared. So we know delta D from before is 235. VI in this scenario is the unknown, so it's not 0 anymore. We're trying to solve for VI. The time in this scenario is something we'll also have to solve for. So in order to solve for this, we have to use this equation over here because we're given the distance. We're given the X value in the question B, which is 425. We're not given time, but we know the initial velocity. So let's solve for time. So time, or let's write the equation out first. So V is d over T. T would equal d over V. So D is X, and X in part B is 425, and the velocity is 58.3. That means T equals 425 divided by 58.3, 7.29 seconds. So we plug that in over here, 7.29, and then make some room over here. And we have plus a half. Acceleration is negative 9.8 times 7.2. Just give me a second here. So 7.29 squared. Okay, so now all we have to do is solve for the initial velocity. So we know that negative 235 equals 7.29 VI. And then we have half times negative 9.8 times 7.29 squared. That gives us negative 260.4. That means negative 235 plus 260.4 divided by 7.29 equals VI. So this is just algebra that we did. We took the 260 to the other side, and then we divided by 7.29 to isolate for VI. So VI equals, plug this into our calculator and we'll get 3.48. So this is positive, that means it will be in the upward direction. So the answer is 3.48 meters per second in the upward direction. That's kind of what we expected it to be when we were trying to conceptually think about what we had to do if we were 425 meters away. Finally, part C of this question asks us, with what speed do the supplies land in the latter case? So in the case of B, what speed do the supplies land? So we have to solve for VF, the final speed. We'll use the kinematic equation. VF squared is VI squared plus 2A times delta D. So this is just another kinematic equation. So it's very useful to memorize the 4 or 5 kinematic equations. So we'll substitute in the values we know. So VF is unknown. VI is what we calculated in the previous question. So 3.48 squared plus 2 times the acceleration, negative 9.8, times the distance, which is given in the equation, given in the question as negative 235. So that's just the height. So we're using the kinematic equation in the y direction because that's where the acceleration happens. We would not use kinematic equations once again in the x direction because there's no acceleration in the x direction. So we'll just solve for VF squared. This will give us 3.48 squared plus 2 times negative 9.8 times negative 235. 4,618 VF. So we'll take the square root, and that'll give us 67.96 meters per second. So that's the final velocity that the supplies reach when it reaches the climber person. So let's look at the attempted solution by the student. So they use the correct kinematic equation and they solve for t, and they plug it back in to the v equals d over t to get 404 meters. Let's just double check what we got up here. So we got 403.7. So this is probably just rounding error based on how many decimal places we kept. For part B, since it needs to be further distance, okay. So they find the time. We got 7.29, so that's correct. So we have 7.29 over here, and then they use the correct kinematic equation to solve, and they get 3.48. So they get the right initial velocity, and then for part C, so 3.48. Finally, they use the right kinematic equation to get the correct answer of 67.96 meters per second. So solution is correct. Great job. Okay, let's get on to the next question. Okay, so what is the strength of the electric field at the position indicated by the dot in the figure? So let's look at this figure. So we have two positive particles and we have a dot, and we need to figure out the strength of the electric field. So let's just draw this out. We have some dot, a positive charge over here, positive charge here, and we have, so between here to here, that's 5 centimeters, sorry. and then between here to here, and then here to here, 5 centimeters, and 5 centimeters. So for a positive particle, the electric field will be on the dot here will be pointing outward. So the electric field line will be over here. So this will be E1. So let's call this particle 1. And this will be particle 2. And then similarly, because it's a positively charged particle, it would point out like that. And then we can try to figure out some angles as we solve. So this would be like this. And because this is a symmetric diagram, we know that the total will be here because the y components of E1 and E2, sorry, I mislabeled this. So this should be E2. The y components of E1 and E2 cancel out because it's a symmetrical diagram and we're left with the x components. So we'll solve here using the following. So to get the distance over here between the two, the positive particle and just the neutral particle here, or the dot, this location, we need to do square root. So let's call this d. So let's say d is the square root of 5 centimeters. So 5 squared plus 5 squared. So this is just Pythagoras theorem because this is just a right angle triangle. One side, so this side is 5, and this side is also 5 centimeters. And this will give us 5 square root 2 centimeters. The equation for the electric field is as follows. E equals K. K is just the electric field constant, and then Q is the charge, and then R is the distance between the two, the location and the particle. So R here, actually I should have labeled this as R. So we already found for R. Q is given in the question, so both particles are 1 nanocoulomb charge. So nano is just 1 times 10 to the negative 9. So here we know K is 9 times 10 to the 9, so this is just a constant. We'll just move this up here. Let's write out some values that we know. So K, 9 times 10 to the 9. This is just a constant, Newton meter squared over Coulomb squared. We know Q is given, so it's 1 times 10 to the 9 coulombs. R is what we calculated up here. So knowing this, we'll substitute these in. So we get E equals 9 times 10 to the 9. Q in this scenario is 9 times 10, negative 9, so this should be negative, sorry. And we have R, 5 square root 2 times 10 to the negative 2, so we're trying to convert this to meters squared. So on top we have 9, on the bottom we have 5 squared, which is 25. Square root 2 squared is just 2. And then 10 times 10 to the negative 2 squared is just 1. So we're left with 9 over 50. Actually, this is times 10 to the negative 4. I missed that component. It will be 50 times 10 to the negative 4. And this will give us 9 divided by 10. 50 times 10 to the negative 4. That'll give us 1,800. Okay, so let's just go back up to the diagram. So we can recognize that this triangle over here is one of the special triangles, so it's one of the special triangles is this, and we know that the angles here and here are 45 degrees. So seeing that this side and this side, so this side and this side are the same, we know that the angle over here is 45 degrees. That means the angles over here is 45 degrees and the angle over here is 45 degrees. So this is 45 degrees and this is 45 degrees. Just basically using the special triangles. We can use sine, cos, but it's just a shortcut. And then now we know that the y component of E1, E2 cancel each other out because the y component over here is going upward, the y component is going downward, and these E1, E2 are equivalent based on symmetry. We only need to find the x component of E1 and the x component of E2. So this direction. So we'll use cos to evaluate. So E total in our diagram is E1 plus E2. So we know E1 equals E2, so we just have 2 times E1, let's say, because they're equivalent. That means we'll get 2 E1 in the x direction. So we know that if this will be in the x direction, so we'll do, let me think about this for a second. So we know we calculated what E is. So we have E cos 45 degrees. So E is over here, what we already calculated based on our formula. So now we've taken the x component, multiplied by 2, because we have 2 electric fields. So we have 2 1800 cos 45 degrees. Cos 45 degrees, let's go back up here. So cos 45 degrees using the special triangle. This would just equal adjacent or hypotenuse. So adjacent is 1 over square root 2. So I'll use this down here. This will be 2 times 1800 times 1 over square root 2. And we end up with 3600 over square root 2 for the electric field. And the units are newtons per coulomb. So what is the strength of the electric field at the position indicated by the dot? So we know the strength is 3600 over square root 2. We can evaluate this as a decimal point in our calculator if we wanted to. What is the direction of the electric field at the position indicated by a dot in the figure? Specify the direction as an angle. So the direction will be in the positive x. So the angle is 0 degrees. So let's go back up here. So the angle is 0 degrees because ET lines up, and we know that the y components of E1 and E2 cancel it out. So let's look at the solution. So they've identified E1 and E2 are equivalent. They calculate using the correct formula, and then they end up with the correct total electric field. They provide the incorrect angle. So the angle for the separate components is 45 degrees, but the angle for the total electric field is 0 degrees. Correct answer for part A. Incorrect answer for part B. Theta is 0 degrees because y components of electric fields cancel. So part B of the solution is incorrect. Okay, so going to the next question. So here we're asked, let's take a look at this. electromagnetic waves ranking. So we're trying to rank electromagnetic waves from fastest to slowest, rank these electromagnetic waves on the basis of their speed in a vacuum. And they're giving us yellow light, green light, X-ray, FM radio, AM radio, and infrared light. So it would be nice to draw the electromagnetic wave spectrum. But for question A, one thing to note that for all electromagnetic waves, the speed will be just the speed of light because it's in a vacuum. So it'll just be 3 times 10 to the 8 meters per second. And this is just c, which represents the speed of light. For B, however, we'll draw out the electromagnetic wave spectrum because we're ranking them based on wavelength, and then C, we rank them based on frequency. So we have to do wavelength in part B and frequency. So let's just draw a simple diagram. So we know the visible spectrum will be somewhere in the middle. So this is the visible. And we have UV on the left, infrared the right, and then we have, I'm just trying to separate these out into lines just to separate them out. We have radio waves, we have FM, and then we have AM. And then on the left side over here we have X-ray, and we have gamma. So gamma is this symbol. So on the right side, we'd have the highest wavelength. On the left side, we'd have the lowest wavelength. On the right side, we'd have the lowest frequency. On the left side, we'd have the highest frequency. So you can see that the correlation is inverse, mainly due to the equation as follows. C is always constant, as we indicated in A. Therefore, F and lambda will be, or the wavelength, so the frequency and the wavelength will be inversely proportional to one another. So on the right side, just to give you a rough number, so on the right side, the wavelength will be around 10 to the 8. On the left side, the wavelength will be 10 to the negative 16. So you can see that there's a range of values. We also have some color for the light. So the colors are in the visible spectrum, so I'll just expand this out. The mnemonic to use to remember the order of the colors is Roy G. Biv, but backwards. So Roy G. Biv backwards. If you're going from smallest wavelength on the left side and highest wavelength on the right side. So R for red, O for orange, Y for yellow, G for green, B for blue, V for violet. So let's just rank these. So we have yellow light, green light, X-ray, FM. So from longest to shortest. So longest wavelength is on the right side. So we can say the AM radio will be the longest. Then it's FM radio. Then we have infrared light. And then we have yellow or green. So we have yellow first, then green. I'll use a different color. So we said AM, FM, infrared, yellow, green. And then X-ray is the last one, and then we have X-ray. So that's the order that it goes. And then for frequency, it would just be opposite. So we start with X-ray, then green, yellow, infrared, FM, then AM. So let's look at the solution. So the correct solution presented by the student for A, and then for B, so from longest to shortest, AM first, they follow the same format, and then frequency is just the inverse, largest to smallest. So the solution is correct. Excellent work. Okay, so next question. In an electrically neutral atom, the number of protons in the nucleus is equal to the number of blank. So for a neutral atom, so this is more of a chemistry question rather than a physics question, but we'll answer it anyway. So for any neutral atom, we have to know that the number of protons is equal to the number of electrons. So this is the answer. Well, let's think about this. So when an atom is neutral, it means there's no positive or negative charge. For any atom, the protons represent the positive charge, and then the electrons represent the negative charge. So if we add up all the protons and all the electrons, and they all cancel each other out, the only scenario that would happen is if they're equal, and that's when we get the neutral atom. The other good way to remember if you're using the periodic table is the atomic number represents the number of protons. So when you read the atomic number, let's say for hydrogen, so hydrogen atomic number 1, that means it has 1 proton. So let's look at the attempted solution. If the proton number and electron becomes equal, the atom is neutral. So they provide the correct answer, and they provide further reasoning. That is also correct. So correct answer and reasoning. Great job. So solution is correct. So next question is, what is the magnitude of the gravitational force acting on the Earth due to the sun? So we're not given that much information. If you were to Google this question, you would get 3.54 times 10 to the 22. So 3.54 times 10 to the 22. But that's kind of not really, doesn't really help us understand why that's the case. So a good way to understand why the gravitational force acting on the Earth due to the sun is 3.54 times 10 to the 22 is to kind of Google the constants for this formula. So Fg is g, the gravitational constant, times mass 1, mass 2, over the distance r squared. So if we were to find the mass of the Earth, the mass of the sun, we know the gravitational constant, and we find the distance in between them, we can calculate this number. So I've already kind of searched for these values. So g is equal to 6.67 times 10 to the negative 11. This is in Newton meters squared over kilogram squared. And then we have m1. Let's say m1 is the Earth mass. This is 5.97 times 10 to the 24. m2 is the mass of the sun. The mass of the sun is much larger at 1.99 times 10 to the 30. So it's multiples of 10 larger than the Earth, which makes sense. And finally, the distance between the sun and the Earth is 149 times 10 to the 6 kilometers, which equals 149 times 10 to the 9 meters. So we're going to take this value, this value, this value, and this value, and we're going to plug them into this equation. So if we had gravity, which is 6, it's not gravity, sorry, the gravitational force constant, 6.67 times 10 to the negative 11, multiplied by m1, which is 5.97 times 10 to the 24, times 1.99 times 10 to the 30, divided by 149 times 10 to the 9 squared. So we get 3.57 times 10 to the 22 newtons. So if we compare it to what the correct answer, so these two are pretty close. So we know we've calculated it correctly. The errors probably are from the estimations of the mass of the Earth and the mass of the Sun and so on. So you can kind of see how we can use the formula for gravitational force to calculate the magnitude of the gravitational force acting on the Earth due to the Sun. And this provides the correct answer. This force is the force which keeps the ground orbiting around the Sun. The gravitational force from other planets does not slightly affect the Earth's orbit. The Earth's gravitational pull on an object depends only on how far away that object is and the mass of the object. So because of the other planets are very far away, the strength of that gravitational attraction is extremely small and can be totally ignored. So that's kind of the explanation of the gravitational force constant. So correct answer, explanation. Good job. Solution is correct. Okay, so next question we're answering is as follows. An object that completes 20 vibrations in 10 seconds has a frequency of blank. So let's define what frequency is. Frequency is measured in hertz. Hertz is just 1 over like a second. So frequency is actually the number of cycles per second. So that's why it's the unit 1 over s, which is hertz. So if we think about this question, an object that completes 20 vibrations, so 20 vibrations is equivalent to 20 cycles in 10 seconds. So 20 cycles divided by 10 seconds gives us 2 hertz. And that's the frequency of that object. So when we think about just what frequency is, we can kind of understand how to calculate the frequency. The inverse of the frequency is the period, which is 1 over t. So that's a good equation to know. So what the period represents is the inverse. So it will be how many seconds does it take to complete one cycle. So how many seconds per cycle? But in this scenario, we only care about hertz, which is the number of cycles per second. So let's look at the attempted solution. So here they follow the same format and they calculate the hertz correctly, the frequency correctly. Correct answer. Great job. Right. So the next question that we have here is an incandescent light bulb produces what kind of visible spectrum? So this is more of a fact-based question. So there's no kind of, there's a complicated answer to this, but the simple answer is it will produce a continuous visible spectrum. So I can see this being a multiple choice question where it gives you 4 options. So a continuous visible spectrum. So let's look at the attempt solution. So an incandescent light source radiates in a continuous spectrum of colors in the visible light section of the radiation spectrum. Being continuous means that all colors are visible in the light because it covers the whole spectrum of visible light, not just certain punctuated emission lines like other light sources. The source of light in an incandescent bulb is similar to the sun's, where the energy output of each is responsible for the light rate. So this is kind of complicated explanation or a complex explanation to the question. The answer is correct, but the most important thing to know here is for an incandescent light bulb, it will produce a continuous visible spectrum. So that's just something that you would want to memorize for a test. So correct answer. Great. So thanks for tuning in today. That's all the physics questions that we will be answering for this session. Hopefully you learned something along the way and found this session useful. If you have any more questions or you want more homework help, you can always visit in the link in the description or go to oneclass.com. Thanks for tuning in again, and I'll see you in the next session. Goodbye for now.